156,164. That is an absolutely staggering number. Between the years 2007 and 2016, that was the average number of annual crashes on icy pavements in the US alone. And tragically, it led to an average of 521 fatalities every single year. So when we hit the road in the dead of winter, the stakes are incredibly high, and the margin for human error pretty much vanishes the second that pavement freezes over.
Which brings us to a really fundamental question. What actually keeps us from sliding off the road? I mean, when you're hurtling down a highway in a 2-ton machine and you hit a sudden patch of ice, what is the microscopic battle happening right there where the rubber meets the road? Is it the grooves, the weight of the car, or is it something completely invisible to the naked eye?
Welcome to The Explainer. Today we're unpacking a fascinating Terra Mechanics study out of Virginia Tech that looks exactly at this phenomenon. Okay, let's dive into this. Because what these researchers discovered about winter tires completely reshapes how we think about driving in the cold. It's a story of hidden physics, extreme engineering, and molecular secrets that are actively working to save your life during your winter commute.
Section 1. The danger of icy roads and the hidden physics of ice.
Okay, so here's the thing. Ice isn't just slippery on its own. When your tire rolls, and especially when it slips, the sheer pressure and heat generated from that friction actually melt the ice. It creates what scientists call a quasi-liquid water layer right in the contact patch. So you aren't just driving on hard ice, your tire is literally hydroplaning on a microscopic film of water that just drastically kills your traction. The physics are completely counterintuitive. The harder your tire works to find grip, the more heat it generates, creating more water and leaving you with way less grip.
Now, before we look at how engineers try to defeat this icy water layer, we need a way to measure their success. In this study, the scientists use a metric called the drawbar pull coefficient, or DPC. Now, don't let this dense Terra Mechanics term intimidate you. DPC is simply a measure of tractive grip. Mathematically, it's the normalized longitudinal force divided by the normal load. But honestly, for the rest of this explainer, whenever you hear DPC, just think of it as our ultimate scientific metric for grip. A higher DPC means your car goes exactly where you want it to. A lower one means you're dangerously spinning your wheels.
Section 2. The secret ingredient: rubber chemistry.
So how do we actually solve the icy road problem? Well, for decades, the industry relied on studded tires, literally driving metal pins into the ice to dig in. But they severely damaged the asphalt and got outlawed in a lot of places. So the industry pivoted to studless winter tires, focusing heavily on the tread pattern. You might be wondering, why not just add more grooves and tiny slits to the tire? Well, those little slits are called sipes, and they're designed to clear away that melted water film we just talked about. And this brilliantly illustrates why more isn't always better. Adding more sipes to a tire eventually yields diminishing returns on friction. You can see friction improves nicely up to about 5 sipes per tread block, but look what happens at 7 sipes. The friction coefficient actually drops off. There's no way around it. You can't just hack the geometry of the tire. You have to change the chemistry.
And that brings us to the hidden variables of the rubber itself. Take a look at the compounds tested here. Their physical density ranges wildly, from 1,094 to 1,157 kilograms per cubic meter. Their specific heat capacity, which basically dictates how they absorb and manage that dangerous friction heat, also varies incredibly across the samples. So modern tire performance relies heavily on these complex, invisible thermal and physical properties.
Section 3. The Terra Mechanics experiment.
To prove exactly how much this chemistry matters, researchers at the Virginia Tech Terra Mechanics Laboratory took 16 tires that, to the naked eye, were completely identical. Same dimensions, exact same construction, identical tread pattern, but they were made up of 8 different secret rubber compounds. Now, valid science requires rigorous real-world simulation to test these differences. Step 1, they meticulously removed the vent spews, those little rubber hairs, and mounted the tires on an actual vehicle, driving them for 100 kilometers just to simulate real-world wear. Step 2, they let the tires rest for 3 days. And step 3, they embedded highly sensitive K-type thermocouples right into the grooves of the tires.
Now, what's really interesting about this setup is the sheer precision. The researchers physically glued 3mm temperature sensors right into the grooves with silicone. Why? Because they wanted to measure the exact temperature spikes happening deep inside the tread blocks as the tire fought for grip on the ice. These highly specialized tires were then loaded onto their single-wheel tester, the Terra Mechanics rig, to see exactly what would happen in a perfectly controlled environment.
And to make this a completely fair fight for the rubber chemistry, the researchers strictly controlled literally every other conceivable variable. They built a custom ice bed, spraying tap water every 2 hours for days just to get the perfect surface. Normal load was locked at 4 kilonewtons. Inflation pressure was strictly held at 193 kilopascals.
The ice bed itself was maintained at exactly -1 degree Celsius, which is a highly treacherous temperature because it's right on the literal edge of melting. And the testing velocity was a very deliberate 0.06 meters per second. The only difference between these runs would be the microscopic makeup of the rubber itself.
Section 4. The surprising results.
All right, so we have the identical tires, the rigorous real-world prep, and the perfect laboratory controls. What happens when the rubber literally meets the ice? Let's track the performance of tire A1 on this curve. On the horizontal axis, we have the slip ratio. This is essentially how much the tire is spinning versus actually moving forward. On the vertical axis, we have our grip metric, the drawbar pull coefficient. As we can see, compound A maxes out with a peak grip around 0.24. Notice how it hits that peak at about a 6% slip ratio, and then as the tire spins faster, the grip levels off and eventually drops.
Let's move to the next set and see how this builds. Now we're looking at tire B1. Remember, same exact tread pattern, same exact ice, but an entirely different rubber chemistry. And wow, the peak DPC shoots up to roughly 0.28. It also peaks right around that 6% slip ratio, but it delivers significantly more grip before it starts losing traction at higher slips. We are visually proving right here that altering the invisible chemistry of the rubber directly and dramatically alters the performance curve on the ice.
But honestly, this next part is the most extreme contrast from the entire study. The researchers tested compound C against compound D. Just look at this difference. Compound C peaked at a measly 0.16 grip, but compound D, it peaked at a massive 0.29 grip. That means the best tread rubber compound almost doubled the tractive grip compared to the worst compound. I really want to stress this again because it's mind-blowing. These two tires had the exact same tread design. The physical difference between sliding straight through an icy intersection and stopping safely was 100% molecular.
So the absolutely crucial point here is this. The researchers found that the compound effect is most prominent in the lower slip region. Why does that matter to us? Well, because the lower slip region, between 0 and roughly 10%, is exactly where everyday vehicles operate during a normal commute. You aren't typically doing high-speed burnouts on the ice, right? You're just trying to accelerate smoothly from a stoplight or maintain control around a gentle bend. And that is exactly where the invisible chemical engineering of your winter tire is working the absolute hardest to grip the road.
We've seen how friction on an icy road creates a highly dangerous microscopic water layer, and how the invisible thermal and physical properties of your tire's rubber are the unsung heroes fighting it off. We've seen that two tires that look totally identical can have vastly different grip levels just based on their chemical compound. So, the next time you face a winter freeze, will you just look at the tread pattern, or will you think about the microscopic chemistry actively keeping you safe?